In the previous videos, we discussed what is meant by singular matrix and what is meant by non-singular matrix, and one theorem I discussed. So just I revised the things. So in the previous videos, I discussed a matrix A is said to be singular if the determinant of A is equals to 0. So any matrix if A is a square matrix, then A is said to be singular if determinant of A is equals to 0. Then we can call here this the square matrix A as singular matrix, and a square matrix A is said to be non-singular if the determinant of A is not equals to 0. Then this we can call it as non-singular matrix, we can call. Clear? So these are the two concepts I discussed in the previous videos, and also I discussed one theorem. So what is that? The theorem is, here it is, A into adjoint of A is equals to, here it is, adjoint of A into A is equals to determinant of A into I to I n. So what is IN? IN is a identity matrix of the order n. So this is the theorem I discussed, and also I discussed the definitions we discussed. Clear? So now my students, in today's class I am going to discuss some more theorems here. So these two theorems here is, for these theorems proof is not required. As for your syllabus, the proof for this is not required. Just the statements we should remember. Clear? So let's discuss that one. So if we'll discuss this theorem. So what is that? If A and B are non-singular matrices of the same order, then AB and BA are also non-singular matrices of the same order. It means, my dear students, if I take one matrix, here it is one square matrix. If I take the one square matrix A, and if that is a non-singular, so what is that? If A and B are non-singular matrices, then if you take the AB, it means if you multiply AB, then after multiplying this, if you consider the determinant of that, means that is the determinant value is not equals to 0. So that is the meaning here. This, if A and B are the non-singular matrices of the same order, then AB and BA are also non-singular. If you take the AB and if you consider the AB's determinant, if you consider that is that value, determinant value is not equals to 0, or else if you consider BA, then that is also non-singular. So very simple. If A and B are non-singular matrices, then if you consider the product of those two matrices and if you consider the determinant value, that is not equal to 0. Even AB or BA, they both are non-singular matrices. So, and A and B are here, this A and B are non-singular matrices of the same order. A and B must be of the same order, you should consider. Clear? So if A and B are the non-singular matrices of the same order, then AB and BA are non-singular matrices. So this is the theorem meaning here. This, so for this proof we are not discussing, just statement result I am considering here, because as for your syllabus, the proofs for these results is not required. Clear? And next question, another one is, the determinant of the product of matrices is equal to the product of their respective determinants. So very simple. So what is that? If A and B, I will consider it is, if A and B are square matrices, if A and B are square matrices, then my dear students, if you consider the product of this, so determinant of AB is equal to determinant of A into determinant of B. This is the result, meaning of this. So the determinant of the product of matrices. So these are the two matrices. Product I am taking, A into B means product I am taking. If you take the product of this, and if you wanted to calculate the determinant means, so this value is equals to determinant of A, determinant of B. So the determinant of the product of the matrices is equal to product of their respective determinants. So determinant of A, determinant of B, and A and B are the square matrices. So this is the meaning of this theorem. Clear? So what is that? Just you should remember, determinant of AB I can write here is determinant of A into determinant of B. So this is the result I have. Clear? And now my students, I am going to discuss as a remark. I am going to discuss. So already we discussed this result. What is that? A into adjoint of A into adjoint of A, adjoint of A into A into adjoint of A, or else adjoint of A into A. This value is equals to determinant of A into IN. So this result I discussed in the previous videos. Now I show that, or we will further make some more results by using this result. So what is that? So for that I am considering here it is as a remark. So one remark we can have. So here it is. I take it as the remark, or you can consider as the, here it is, another one theorem also you can consider. So here, clear. So now my students, I will consider this. We know that. So we know that, here it is. What about we know? We know that A into adjoint of A is equals to here. Or here it is, or adjoint of A into A is equals to determinant of A into I to the power n, where IN is the identity matrix of the order n. Clear? And now my dear students, I will consider the, here it is, first term and third term. In this I will consider this and this. So this I can write here, it is A into adjoint of A is equals to determinant of A into IN. I am considering this and this. And now my dear students, I will take both sides. Here it is determinant. Taking determinant, both sides. Both sides I will take the determinant. So if you take the determinant means what happens here, it is A into adjoint of A, here it is, into determinant of A into IN. So both sides I am taking determinant. So after taking determinant conditions, this I can write here, it is determinant of A into adjoint of A is equals to, here already I consider here, or else first we will discuss the result. So what is the result? We know that in the earlier videos we discussed. So here it is, we know that determinant of K into A is equals to, if A is of the order n, then determinant of K is equals to K to the power n, here it is, here it is K to the power n into determinant of A. This we discussed in the previous videos. So determinant of K is equals to K to the power n into determinant of A. I think in the properties of determinants I given to you this result. So determinant of K into A can be written as K to the power n into determinant of A. If A is of the order n, then we should use this result. The n is, where n is the order of the given A, whatever the matrix we have A, so that order is clear. So K to the power n into A. So now my dear students, you can consider, I am applying the same result here. This. So here what I do, I will consider this as K. I am considering this K because K is nothing but the constant. K is any constant. So determinant of A means what? If you solve any determinant, you will get one constant number you are getting. So therefore this determinant of A, I am taking it as K, and IN is nothing but, it is nothing but the square, it is nothing but the identity matrix. It is the one matrix we have. So therefore this value I am considering it as K, and this IN I am considering it as A. Clear? So now apply this result. So after applying this result, I can write here it is K to the power n. So whatever I am solving here it is, this is IN means, so here it is where A is the matrix of the order n. So here I am discussing for the n order. So therefore here it is, so K, determinant of K into A can be written as K to the power n. K means what here it is? K means here it is determinant of A. So therefore determinant of A whole to the power n into determinant of, here it is, A means A is determinant, but here it is instead of A what I have? IN. So therefore determinant of IN. This result I applied here. Clear? And now my dear students, this can be written as, already I told you what is that? A determinant of A into B can be written as determinant of A into determinant of B. Like that, determinant of A into adjoint of A can be written as determinant of A into determinant of adjoint of A. This is equals to, here it is, determinant of A whole to the power n. And this, my distance, determinant of IN value is 1. If you consider any identity matrix of any order, that value of the determinant is equals to 1. So determinant of IN is equals to 1. 1 into anything is itself. So therefore I am writing here this determinant of A to the power n. You can write here this determinant of IN is equals to 1. Clear? So now this can be written as, if you shift this determinant this side means that will goes to the denominator. So denominator means determinant of A whole to the power n 1. If you take numerator, that will become determinant of A whole to the power minus 1. So therefore here it is determinant of adjoint of A is equals to determinant of A whole to the power n minus 1. Because you can observe here this. So or else I will write another step. So determinant of A whole divided by determinant of A. This determinant shift to the, you can take the denominator. So this can be written as determinant of A is equals to adjoint of A is equals to determinant of A. So here it is determinant of A whole to the power n, and here it is nothing is there means 1. So this, if I take numerator means that will become minus 1. So therefore n minus 1 I can write. Clear? So therefore here adjoint of A is equals to determinant of A whole to the power n, where this is, or else where this is for the nth order. So this is for the nth order. You can consider for the nth order. So if your, here it is, if you have the matrix of the nth order, so then if you have the nth order matrix, then a determinant of adjoint of A is equals to determinant of A whole to the power n minus 1. Clear? So this is the very very important result, my dear students. And now, my dear students, if you have the, here it is, if your determinant, if for example, if your A is of the order, if A is of order 3 cross 3, or if A is the order 3, then adjoint of A is equals to determinant of A, 3 minus 1 is nothing but determinant of A square. Adjoint of A is equals to, here it is, determinant of A whole to the power n minus 1. Here it is for nth order n minus 1, it means 3 minus, here it is A is of the order 3 means 3 minus 1. So therefore determinant of A square. Like this you can write. So what is the result here? This, so determinant of adjoint of A is equals to determinant of A whole to the power n minus 1. So this is the formula for the nth order. Now, my dear students, you can generalize like this. So again, another one result you should remember. So what is that? The result I can give to you is, here it is, adjoint of A is, we can written as, here only determinant of adjoint of A can written as determinant of A whole to the power n minus 1. But if I given to you determinant of adjoint of A means, so this value is equals to determinant of A whole to the power n minus 1 whole, here it is, whole square you should write, n minus 1 whole square, because determinant of adjoint of A. How many adjoints are there in the determinant? Inside the determinant, how many adjoints are there? 2 adjoints are there. So therefore then this value is equals to determinant of A whole to the power n minus 1 whole square. Clear? So if only one adjoint inside the determinant, if only one adjoint there means this value is equals to determinant of A whole to the power n minus 1. If 2 adjoints are there means determinant of A whole to the power n minus 1 whole to the whole square. If you required adjoint of, here it is, adjoint of A, here it is, adjoint of A means this value is equals to determinant of A whole to the power n minus 1 whole cube. So these are very very important, as for if you consider for the, if you are wanted to write the competitive exams means there these results are very important. Please, clean observation is very important. Please remember what I am telling to you here is, so determinant of adjoint of A, if A is of the nth order, then this value is equal to determinant of A whole to the power n minus 1. So if A is of the order 3, then adjoint of A is equals to determinant of A whole square, that is 3 minus 1. If you are confusing means here it is, this is example for this result, but the next result what I am giving to you here, this is, so this is the result where adjoint of A, determinant of adjoint of A is equals to determinant of A whole to the power n minus 1 whole square. So determinant of A whole to the power n minus 1 is common for all the adjoints, and here the power n minus 1 whole square, the power of n minus 1 whole power is raising depends upon the adjoint. Here only one adjoint is there, so determinant of A whole to the power n minus 1. And determinant of adjoint of A is equals to determinant of A whole to the power n minus 1 whole square, because two adjoints are there. So therefore n minus 1 whole square. If 1, 2, 3, if 3 adjoints are there means this can be written as determinant of A whole to the power n minus 1 whole cube. So like this you should remember. These results are very important. Clear? So these results useful while solving the CET or competitive exams. These results are important. So please try to remember these results. Clear? So this is the result I proved by yesterday's theorem. Whatever I discussed, this we know that this result I took from the yesterday's, I mean previous videos class. I discussed this theorem. So depend upon that I wrote the result here it is, and by using this I have these results. Clear? So please pause the video to note it down. So please clearly observe what I am writing here is. Clear? So please pause the video to note it down. Still if you have any doubts you can comment me, I will reply for that. So please note it down. So next concept we are going to discuss is inverse of a square matrix. So what is inverse of a square matrix? That we discussed in the previous videos. So just I recall the things. So my dear students, let us consider the one matrix A here. So if I consider the one matrix A, then my dear students, if there exists inverse means what here it is? If A is a one matrix, if there exists another one matrix B, such that AB equals to or BA is equals to identity matrix, then in this case we can call here is B is the inverse of A and A is the inverse of B, you can call. So for any matrix A, if there exists another one matrix B of the same order, then if you multiply, after multiplying these two, if you are getting the identity matrix, then this we can call it as the inverse of A, and or else you can call it as the invertible. So here A and B are invertible to each other. So or else you can write like this, or else my dear students, this B you can write here this way, or the B you can write here this as symbol like this. A inverse also you can write. So either you can write like this, or A into A inverse is equals to, or A inverse into A is equals to I. So where I is the identity matrix. If this condition is satisfied, then you can say here this A and B are invertible to each other, and B is called the inverse of A and A is called the inverse of B. So my dear students, please remember. So if A is any matrix, then if there exists another matrix such that AB is equals to B is equals to I, then B is called as the inverse of A, or else A is the inverse of B. If this like this you can call. So this B is nothing but what? A inverse. Clear? So this is the inverse of a square matrix. So this concept already we discussed in the earlier classes. Clear? And now the next theorem we have. So what is the theorem here? The theorem is here, my students, a square matrix A is invertible. A is invertible means what? So here in this case A is called as the invertible. So a square matrix A is invertible if and only if A is a non-singular. It means, my dear students, they are telling that a square matrix A is invertible. So in any here this A is invertible if and only if A is non-singular. So whenever A, here it is, the meaning is whenever A is invertible, I mean if there exists an inverse, then in such case the here this determinant of A is not equals to 0. Clear? So A inverse exists if and only if now A is non-singular. Non-singular means what? A is non-singular means determinant of A is not equals to 0. So A inverse exists, my dear students. The meaning of this, generally the meaning of this is A inverse exists if determinant of A is not equals to 0. If determinant of A is not equals to 0, then only the A inverse exists. So this is the meaning of the given theorem. So to prove this, what I do, my dear students? So please remember another one condition given here. What is that? If and only if. So many times we solve such type of questions. So already I told you, in the statement whenever you have if and only if conditions, in that case you should take here this, you should prove by two parts. What is that? First you should consider if part. So first you should consider the statement here. What is that? Here this A is square matrix. A is a square matrix, A is invertible. A square matrix A is invertible. So this is the one part you should consider. And if another one part is A is non-singular matrix. So whenever you have if and only if condition, first you should consider this statement and you should show this condition. And after here this conversely you should take this part and you should end up with this result. So this we can call it as if and only if. So if and only if whenever you have in the statement, then first you should consider the first statement and then you should complete, you should end up with the second statement result. And next you should consider this, conversely you should consider this result and you should prove this result. Clear? So that is the very important. Whenever you have in the statement if and only if, you should consider first here it is whatever you have. First you should consider this statement, that is you can call it as the if part, and then you should consider if and only if part. This part you should consider. First you have this. Whenever you have if and only if conditions, in that you can divide the statement into two parts. So this is I can call it as the first part and this I can call it as the second part. Clear? So while you go to the higher classes, that time you will come to know if and only if why should we use such this type why should we solve, that you will come to know in your higher studies. But as of now, whenever you have if and only if conditions, the statements we use will divide into two parts. First, what is the whenever if you have the if and only if condition means what should you do? First consider the first part and prove that and end up with the second part result. And next conversely you should take the second part and you should end up with the first part. If you do so, then your proof is valid. Clear? So for this reason what I do? First I will consider. So let us consider. So here it is. Let us consider A is a invertible. Let A is invertible. So if A is invertible means according to our definition what it indicates, my distance. If A is invertible means here it is. There exists if A is invertible. So this implies that AB into BA is equals to I. So it means what it indicates, my students. Let A is invertible. So if A is invertible means there exists another one matrix B such that AB is equals to BA is equals to I. So like this I can write. And now, my dear students, what I will do here is I should show that A is non-singular matrix. So by this I should show that A is non-singular matrix. So first what I will do, this and this I will consider here this. So this AB is equals to I will take, and now I will take both sides determinants. I am taking determinants because my aim is to prove that A is non-singular. By using this A is invertible, by using this condition, I should prove that A is non-singular matrix. A is non-singular matrix means what should I show? Determinant of A is not equal to 0. This is my aim. To prove this, what I will do? I will take both sides determinant. So taking determinant, so you can write here it is, or else you can take here it is, taking determinant both sides. Taking determinant both sides. So if you take determinant both sides, what happens? Determinant of AB is equals to determinant of I. And now in today's session only we discussed determinant of AB can be done as determinant of A into determinant of B is equals to. So what is this? Determinant of I is nothing but here it is 1. Clear? So and now my students, this implies that so for any two constant numbers, if you take the product of this means this is equals to 1. This is possible only if determinant of A is not equals to 0 and determinant of B is not equals to 0. Suppose if this value is equals to 0 means 0 and anything is 0. So LHS is not equals to RHS. If you take B, determinant of B is equals to 0, if you get the value means, so this is also this G, if you take determinant of B is equals to 0 means 0 and anything is 0. So 0 is not equals to 1. 0 is not equals to 1. So therefore what happens here is sum of these here is determinant of A and determinant of B should not be equals to 0. If these two values are not equals to 0, then only this product is equals to 1. So therefore determinant of A is not equals to 0 and determinant of B is not equals to 0. So this implies that from this I can write here is determinant of A is not equals to 0 means what it indicates? This indicates that determinant of A is this indicates that A is non-singular. A is non-singular. So what is my aim? If a square matrix A is invertible, if and only if A is a non-singular matrix. So what I consider here is first I consider this first part. Let us consider A is invertible. After considering this, I proved that here it is A is non-singular matrix. Clear? And next questions. Conversely means I should whatever I have proved here is this I should take the reverse again. I should take the reverse part here. So for that is what I do. Conversely, what I take? I take now I take this part and I prove here is this result. Second part I am taking here is if A is a non-singular matrix. So here it is. Let us take here it is. I'll take here it is if A is non-singular matrix. So this implies that. So if A is non-singular matrix means what it implies? It implies that determinant of A is not equals to 0. And let us consider, we know that just only we need to prove the results. What is that? A into adjoint of A is equals to adjoint of A into A is equals to determinant of A into IN. Clear? So this result in the previous videos I have proved here is. Now I consider this and this. So this implies A into adjoint of A is equals to determinant of A into IN. Clear? And now my dear students, here I will divide determinant both sides. So divide determinant both sides. If you divide means you will get A into here it is adjoint of A whole divided by determinant of A is equals to determinant of A whole divided by determinant of A into IN. So this determinant got cancelled. So this implies A into adjoint of A whole divided by determinant of A. Clear? And this is equals to IN. Clear? So now my dear students, A into something is equals to IN. It means identity matrix you are getting means. So this can I call this as the inverse? Can I call this as inverse? So it is A into here. A into I am considering here it is. Sorry, this make it as capital A. Clear? So A into here it is. So A into in this place it is A to the element A after multiplying some element, say whatever may be the value of this. So to this matrix, to this A, I am multiplying with adjoint of A divided by determinant of A. So after multiplying with this value, I am getting identity matrix. If I am getting identity matrix means this will act as the inverse. So therefore, where here it is, this will I can call it as here it is A inverse, because we know that A into after A to the matrix A, if I multiply with any one matrix, any one value, if I am getting identity means this in this place whatever I have that I can can call it as the inverse. So therefore here it is, this is of the, I am comparing, or else you can take like this. So this is of the form A into A inverse is equals to I. So in this place A inverse you have this value. Clear? So therefore you can call here it is where A inverse is equals to. So what is that? A inverse is equals to adjoint of A whole divided by determinant of A. So clear? So now my dear students, this I can call it as A inverse, because A into some value multiplying this you are getting identity matrix, means this I can call it as inverse. So what is inverse? This I can call it as A inverse. So A inverse is equals to adjoint of A divided by determinant of A. So therefore this implies that here it is in the here it is in A inverse is equals to adjoint of A divided by determinant of A. So this implies that determinant of A should not be equals to 0, because if determinant of A is equals to 0 means, my dear students, this A inverse does not exist, because if determinant of A value is equals to 0 means anything divided by 0 is not possible. For that reason, this determinant value, this determinant A value should never be equals to 0. So what is if determinant of A is never be equals to 0 means what it indicates? This implies that A is non-singular. So this implies that A is non-singular. So therefore, my dear students, what I consider here is, if A is non-singular matrix, then I concluded here it is. If A is non-singular matrix, then A is invertible. So this is the case, but here it is, usually I don't write this, so directly you can call here it is A is invertible. So a square matrix A is invertible if and only if A is non-singular matrix. So I consider here it is, if A is a non-singular matrix, then A is invertible, because A into A inverse is equal to I you are getting. So therefore here it is, this is A inverse value. So it means, what it means here it is, if A is non-singular, then only invertible exists, means there exists a one matrix such that this element this matrix is equal to IN. Clear? So therefore like this you can prove. Usually the proof of this they won't ask, but for knowledge purpose you should remember. But always remember this result. So whenever you have the matrix A, your square matrix A you have, if A is invertible, then only here it is. If A is non-singular, then only A inverse exists. So what is A inverse, my students? Please remember, this is very important formula. To find the inverse, I am going to use in future. So what is that here it is? So A inverse is equals to, if you wanted to find A inverse means A inverse is equals to adjoint of A divided by determinant of A, and where determinant of A never be equals to 0. Clear? So therefore A inverse exists if A is non-singular. A is non-singular means what it indicates? A is here it is, A is non-singular means determinant of A is not equals to 0. So as of now, whatever I explained here it is, the entire meaning of this is A inverse is equal to adjoint of A divided by determinant of A if and only if determinant of A is not equal to 0. So in this case, determinant of A should not be take the determinant of A value never takes 0. If it takes 0, then A inverse is not possible to find. So for that reason, so just remember, so if you are getting confused with all this means, just forget it all, just remember the result. And what is the meaning of the result means, whenever you are going to find the A inverse, you have the formula. What is the formula to find the A inverse? A inverse is equals to adjoint of A divided by determinant of A, and the result and the condition is determinant of A not equals to 0. Determinant of A is not equals to 0 means the meaning is A is non-singular. So therefore, whenever you are finding the A inverse, that case you should check whether A is non-singular or singular. Clear? So this is the result. So usually they don't ask in your annual examination, in Karnataka board examinations, usually they generally they don't ask the proof for this. But still I explained here to understand the concept, knowledge purpose. Clear? So just remember this result and solve the questions. Clear? So if you are getting too much confused in this means, please leave the proof. Just remember the result. So if you want to know the proof again, if you want to know proof means, please comment me. I will reply for that. Clear? So I hope you understood. In the next class we will discuss with some more concepts. Thank you.